Hello, everyone. Thanks for coming to this talk. This is an extended version of an in-person talk at ITCS 2025, which will be held at Columbia University. I'll be presenting our work on online balanced allocation of dynamic components. This is joint work with my advisor, Rajmohan Rajaraman. So first, I really want to motivate this problem and tell you a little bit about why we ended up studying this. So we all know that large-scale big data applications are inherently distributed. And what this means is that the resources required by such an application are so large that uh, one eventually has to go to the cloud and lease out certain virtual machines for such an application. And there's no single virtual machine which can basically store the whole application, and the application itself is spread across different virtual machines, and this leads to inter-virtual machine or inter-VM communication. And the main question is that do we have a principled way to allocate resources? Here, the resources are virtual machines in a very demand-aware and dynamic fashion, so as the congestion and bandwidth and latency are actually minimized, right? And what we know is that inter-VM communication is cheap if VMs are in the same physical cluster or the same location, else they can be costly. So in this diagram here, there are these servers S1 through SL, which host different virtual machines. And the red edges denote some form of communication that's going on between virtual machines, which are labeled in blue. And communication which happens between two virtual machines in the same server or in the same cluster are relatively cheaper than the communication that happens between virtual machines which are scheduled in different clusters. Okay, and we also know that most of the virtualization systems, they support live migration of VMs, which means that based on the communication patterns between different VMs, it's possible to migrate some of those VMs so as to minimize the communication costs. And in practice, VMs are allocated and deallocated over time. The startup cost of a new virtual machine is just proportional to its size, right? And ideally, what we would like to do is we want to migrate a virtual machine as little as possible throughout time until it's eventually deallocated. And one of the questions that we wanted to ask in this work is, can we ensure that the number of clusters that we're using scales with the number of allocated virtual machines at all times? In other words, is there a tight and balanced packing of virtual machines? Such a packing has potential applications in energy savings, and this can lead to huge optimization uh, in terms of reducing the energy costs. And there are two sources of uncertainty here. The first source of uncertainty comes from the fact that we do not know how long a specific virtual machine is going to be in the system, because this is really dependent on an application's or user's requirements, which change and fluctuate over time. And the second source of uncertainty comes from the fact that we have the inter-VM communication patterns are unknown in advance. So, motivated by this concrete practical application, we introduce the online balanced allocation of dynamic components problem in this paper. In this paper, in this problem, we have a setup, as follows. So there are L clusters denoted by S1 through SL. Each of these clusters have a capacity K, which you can think of as an integer. And there is a dynamic set of vertices of at most K times L vertices at any time T. And the system starts at time T equals 0. Initially, there are no vertices in the system. And let us define the notion of a component here. So by a component, we mean, and we refer to a set as a set of vertices. The vertices correspond to virtual machines here. Uh, all vertices in the same component must be assigned to the same cluster. Okay, so this captures in some sense that we want uh, machines which are frequently communicating with each other to be assigned to the same cluster. And now in the online world, we have a request sequence which is revealed to us over time, and the requests correspond to three different types. So the first type of request is an insertion of a vertex, which is just a singleton component containing that vertex. The second type of request can be a deletion of a vertex from its existing component. And the third type of request is a merge request, where such a request is between two vertices which are contained in components CU and CV, which must be merged and then co-located thereafter. The insertion and migration cost is 1 per vertex, and we can actually generalize it to weighted and non-uniform uh, costs in general. Okay, so we're in the competitive analysis realm, and what this means is that we are interested in algorithms which are, let's say, row competitive. And what row competitiveness here means is that we want the cost of our algorithm on any request sequence sigma to be at most row times the cost incurred by an optimal offline algorithm, uh, modulo an additive constant, which is independent of the request sequence sigma. Okay, so it's a very standard framework to study online algorithms. Okay, so in our setup, we'll also allow over provisioning of cluster volume. This is basically done to obtain polynomial time algorithms. And more specifically, we assume that each of the L clusters has an extra volume of epsilon k for some small constant epsilon, which is at least 1 over k. All right, well, this makes sense because when we talk about extra capacity, we want at least one extra vertex plus per cluster. So that's where the lower bound on epsilon comes from. And here we measure competitiveness against an optimal offline algorithm, which has a similar amount of resources. And this is a strictly stronger benchmark than resource augmentation, where competitiveness is analyzed with respect to an unaugmented optimal offline algorithm. Furthermore, we require our online algorithm to be also resource competitive. And what this means is that we want to capture the practical objective of utilizing a few number of clusters at any given point in time, so as few as possible. And we want to compare the resource usage of our algorithm with respect to the best optimal offline algorithm. And we say that an algorithm is mu resource competitive if the number of clusters that it uses is within a mu factor of the clusters that are used by the optimal algorithm at any point in time. So now we're ready to present our main result. So in this paper, we show that there is a deterministic algorithm, which is log k comparative, and it's 2 plus epsilon resource comparative for online balanced allocation of dynamic components with 1 plus epsilon over provisioning. So this means that there is an extra volume of epsilon k that is allowed on each cluster, and this is allowed to both the online algorithm and the optimal offline algorithm. So one remark that I want to make here is that we can actually recover the same competitiveness um, in but we can actually obtain a better resource competitiveness in the 1 plus epsilon resource segmented setting. Recall that in the resource segmented setting, the optimal offline algorithm is constrained to a capacity of k per cluster. Moving on, we show that any randomized algorithm for OBADC with 1 plus epsilon over provisioning must be at least log k comparative, where epsilon is a constant between 0 and 1. So I want to highlight some of the challenges we faced in obtaining the algorithm. So the first challenge is that, in this dynamic uh, environment, deletions of vertices can cause repeated migrations of components because our objective really is to minimize the number of active clusters while minimizing the total migration cost over time. So suppose that you have a setup like this where we have a few clusters containing some components, and we have a green component which is resized as a result of vertex deletions that are happening. Now, in this case, once all vertices in the green component are deleted, just to minimize the number of clusters used, we might wish to move the yellow component to some other cluster. Okay, so this already introduces some dependencies between component assignments. And in general, a migration of a component could depend on other components that are either increasing or decreasing in size. Okay. And we require intuitively an assignment of components which is robust. What does that mean? Well, we want an assignment which does not change too much after a merge, insertion, or deletion of any component, right? And we do this by committing to a configuration of components which satisfies certain invariants or conditions at any given point in time. Here's a rough outline of our structure. Here you can see that we have assigned large and small components labeled in blue and green respectively, and we have kind of packed them tightly, right? So before I move on to describe the specific properties of our component assignment, let us distinguish between small and large components. So a component is said to be small if its volume is at most epsilon k over 4, and otherwise it's a large component. For large components, we solve an integer linear program to minimize the number of clusters that are used. And small components can be thought of being greedily assigned in a first fit fashion to all the clusters. And we'll go back to this component assignment, and we'll go in more detail shortly. The main challenge is that we want to maintain such an assignment after component merges and deletions, and we want to minimize the total migration cost that can be incurred. So let's actually zoom into a slightly easier problem. And it's a slightly simpler case where there are only insertions, and we can also disregard resource competitiveness in this discussion. So the interesting thing is that even in the insertions only case, where we're not insisting on resource competitiveness, the lower bound of log k still holds. Okay, so let's try to sketch out an algorithm for this case. So here we again have a classification of components into small and large. We further classify components into various component classes, such that C is a class I component if its volume is at least 1 plus epsilon over 4 to the I minus 1, and at most 1 plus epsilon over 4 to the I. It can be easily seen that the number of small component classes is log k, while the number of large component classes is roughly constant, right? So this order sub epsilon notation hides epsilon factors. Okay, so next we define the notion of a signature. So a signature roughly captures a specific component assignment on each cluster. Okay, so what this says is that it's a vector of dimension equal to the number of large component classes, such that the total volume intuitively that can be assigned with respect to the signature is at most k. And for the sake of simplicity, we can think of D as roughly epsilon over 4. It follows that the number of signatures is only a constant depending on epsilon, and the reason is that uh, there are only roughly 1 over D components, large components that can be assigned on any cluster, and uh, this just bounds the total number of signatures by considering all possible uh, values for the entries of the signature vector. Okay. So let's now consider how we can write down a mathematical program or an ILP to solve uh, uh, the convex program and assign signatures so that we can assign large components to different clusters. Okay. So first of all, note that the definition of a signature takes into account it's only valid for large components. So right now we don't bother about small components at all. Okay. So let sigma j be the number of large components, uh, the number of class j large components over here. And so now our goal is to write down an ILP. So let T denote the set of all possible signatures, and Ti is, let's say, some signature. Okay, so if you write down this ILP, it's relatively simple. What it's just saying is that we want to assign signatures to different clusters in a way such that the number of large components of each class kind of match the assigned signatures. Okay, so this is our ILP. We're really, though, interested in how much the ILP solutions change when a merge happens. And the key observation is that at most 3 entries in the right-hand side vector of this ILP change. If we invoke a well-known result in sensitivity analysis of ILPs, we can show that the change in ILP solutions is roughly constant if we change the number of large components of any class by a constant number. And then we can do a simple greedy assignment of signatures to clusters to bound the total volume of components that needs to be migrated after any merge by roughly order k. Okay. So now let's discuss a little bit about how we are going to charge the cost uh, of this algorithm to various vertices. So first recall that each class I component is assigned a volume of 1 plus epsilon over 4 to the I on the cluster that it is assigned to. And now let's consider a merge of two components, Ci and Cj, which are allocated in different clusters, and they're merged into a larger component called Cm. Okay, and without loss of generality, let's assume that J is at most I. We have two cases to consider. In the first case, Cj actually fits on Ci's cluster, right? In this case, the intuitive thing to do would be to just migrate the smaller component Cj to the cluster containing Ci, and then we can just charge this migration cost to vertices in Cj, right? The other case is when Cj does not fit on Ci's cluster, right? Because it might happen that Ci's cluster is nearly full. In this case, however, we cannot just migrate vertices in the smaller component Cj. We have to actually also migrate um, vertices in Ci to another cluster, right? We pay a cost which is roughly equal to the sum of Ci and Cj, but now we note that vertices in Ci are also part of a component which has a larger component class, whose component class is at least I, where I is at least j. So in this way, by using this observation, we can charge this migration cost, which is equal to the size of Cm to all vertices in the component Cm. So now, since the number of small component classes is at most log k, each vertex can only be charged log k many times in this manner. And the total amount of charge in vertices for small component merges is roughly n log k, right? So this already gives us a log k competitive algorithm, assuming that components always stay small. But based on our ILP sensitivity analysis, it's relatively straightforward to account for the case when merged components are large. So recall that we showed that whenever a large component is created, a cost of roughly order k might be incurred. But on the other hand, a large component has size at least epsilon k. Hence, whenever a large component's class increases, we can charge this migration cost to all the vertices in that component. Since there are only a constant number of large component classes, each vertex in the large component can be only charged a constant number of times. As a result, the total charge on any vertex is bounded by log k, right? So this implies log k competitiveness because an optimal offline algorithm pays at least a cost of n for n vertex insertions. So now let's move on to the more general case. And this is where we will face some significant technical challenges. So the first thing is that to note is that in the previous argument, we ignored resource competitiveness completely. But that's a relatively simpler problem to fix. So we can first introduce a minimization objective in our ILP, which is going to minimize the number of clusters that are used to place large components. However, we also need to assign small components in a way where we don't waste too much of the space in each cluster, right? So as mentioned earlier, the main challenge is to ensure that such an assignment can be maintained dynamically, right? And that such an assignment is also resource competitive. Our charging arguments and analysis of this algorithm is fairly complicated and intricate, but in the next few slides, I will try to give you the high-level ideas of our analysis. So we'll describe some of the ideas and invariants that are maintained by our algorithm to this end. So the first idea is that we want a more fine-grained categorization of components when assigning volume on clusters. So one of the invariants that our algorithm maintains is that the size of the assigned volume of any component on any cluster is at most a constant factor of its actual size. So this constant factor is roughly 1 plus epsilon over 4. And let C be a class I component such that the size of C is at least 1 plus epsilon over 4 to the I minus 1, and so on. So for all classes I and any class I component, our algorithm ensures that one of the following statements hold. And I think it will be more instructive to demonstrate this pictorially than looking at this invariant. So I'm going to move on to the next slide. So here we see that so in this diagram, we have 4 different cases, right? And we have essentially broken down the assigned volume uh, of class I components into 4 different chunks, which differ by a slight multiplicative factor. And uh, the shaded regions correspond to the actual volume of the component, while the non-shaded regions taken together with the shaded regions correspond to the total volume that's assigned to such a component. So what this invariant ensures is that at any given point in time, if let's say our component has volume between AI0 and AI1, then the amount of assigned volume to this for this component is at most AI3, and so on and so forth, right? So as the actual volume of a component increases, the assigned volume increases slightly to make sure that it's always within a 1 plus epsilon over 4 factor. Okay. So this also holds in the case of vertex deletions. So the reason why we are doing this is not to ensure that the assigned volumes upper bound the actual volumes. It's in fact to ensure that even under deletions, we have a relatively stable way of assigning volumes to every component. Okay. And the second idea is to actually maintain the set of all clusters which are almost full. We call them the mark clusters. Intuitively, a mark cluster is one for which the algorithm is unsuccessful when assigning volume to a small component. What this means is that if a small component uh, was required to be assigned volume on some component, and the algorithm found out that the residual volume is insufficient, then that cluster is marked. So recall that a small component is size at most epsilon k over 4. The maximum assigned volume of a small component is only epsilon k over 3. So this means that a marked cluster has at most epsilon k over 3 residual volume, right? And this implies that at least k vertices are assigned on each marked cluster. So once a cluster is marked, we know that we are actually utilizing space in this cluster fairly well. Okay, so moving on, we define the set of active clusters to be the set of clusters such that at least one vertex or one component is assigned to it. Okay, so let's let SL and SS denote the set of clusters such that there's at least one large component assigned to any cluster in SL. And SS is the set of clusters which only contain small components, right? So second invariant that our algorithm maintains is directly captures a tight packing of components. So if at any given point in time, the number of clusters holding small components is actually non-zero, then this means that either the set of clusters holding large components is empty. That means that there is no large component, or all the clusters in the set of large components are marked. Or it is the case, and it is the case that exactly one cluster in the set of small clusters is unmarked. Okay. Pictorially, this can be illustrated as follows. So in the first diagram on the left, we see four clusters which are assigned to which large components are assigned. And there only three of them contain small components, right? So in this case, we don't so in this case we see that there is no small the set SS is actually empty, so the invariant is satisfied. While in this on the figure on the right hand side, we observe that we have tightly packed components into all the clusters, such that there is only one cluster on the right which is assigned small components. And this will be the unmarked cluster. Note that all of these clusters are almost full and are likely to be marked. Okay, and the final idea is to use some kind of laziness, which implies that we don't solve the ILP very frequently under vertex deletions and reinsertions, because this can be very costly and it can incur an order k migration cost. So suppose that a large component of class I becomes a class I minus one component, or it becomes a small component. Then the idea is to simply only resolve the ILP once at least an extra epsilon square k vertices are deleted from that component. This implies that, some class I minus one components are actually considered class I by the algorithm. So what it means is that the volumes could be slightly overestimated for some large components. However, this is still fine because the number of large components that can be assigned on any cluster is 1 over epsilon. And so if a cluster is marked, the total number of vertices assigned to it is still at least k. Okay. So this is basically what our algorithm ends up doing, is that even if a cluster becomes a class I minus one component, the assigned volume of a cluster of that component is still sufficiently large. And on the other hand, it's still considered a class I component, right? Okay. So next, let's move on to discuss how we ensure resource competitiveness. So as mentioned earlier, when vertices get deleted from a component, this has an effect of increasing the residual volume on our cluster. So in this diagram, we can see vertices in the third cluster and the green component, let's say, being deleted. In this case, we would like to move the vertices in the green vertices in the fourth cluster to the third cluster, just to ensure that we do not use a large number of clusters to assign components. So to ensure resource competitiveness, we migrate small components from an unmarked cluster whenever it's possible. At any time t, the dynamic component assignment essentially mimics a feasible assignment, which can be thought of assigning components in the following fashion. So first, we can think of assigning all these large components via the ILP approach that we highlighted in the previous slides. And after the large components have been assigned, we can assign small components greedily in a first fashion. Okay. Interestingly, what we show is that such an assignment utilizes at most 2 plus epsilon times more clusters as compared to opt in the worst case. Okay, so let's discuss some of the charging arguments that involve deletions. So the first idea is that whenever a vertex V gets deleted, we leave a credit of roughly a constant amount and distribute it uniformly to all vertices in V's component. This implies that once a constant fraction of vertices in a component are deleted, there's an extra credit on each surviving vertex. We also leave an extra credit to pay for rebalancing costs of small components. Okay, so our charging argument basically assigns a credit of roughly log k to each vertex on its insertion. And let C denote the component of V throughout time. The credit on V is used to pay for the migration costs incurred each time C's assigned volume or its class increases for the first time, necessitating the migration of V. It's also used to pay for the credit that's assigned to vertices in C upon V's deletion. Finally, it's some of the credit that's assigned to V is also used to assign to handle various rebalancing costs. Okay, so this implies that each time C's component class or assigned volume decreases, V has enough credit to pay for a corresponding future increase. Hence, we can restrict our attention to only monotonic increases in component classes or assigned volumes. And this is very similar to the insertions only case. By generalizing this argument, we can show that our algorithm is log k competitive. Okay, I want to just do a quick illustration of the charging of the ideas behind our charging argument, because this is something that is also used in our algorithms with predictions, which I'll describe shortly. So this diagram on the right shows the evolution of a component C over V's lifetime, right? So V is inserted at some time, it's deleted at another time, and let's denote the component that V is contained in by C. So you can see in this diagram that the class of C can actually increase and decrease over time, and can increase and decrease so arbitrarily. But every decrease in C's component class can be actually paired with a unique component increase or a change in C's assigned volume. And this bijection helps us to account for the extra credit that's needed to handle every corresponding increase after a corresponding decrease in C's component class or assigned volume. The monotonic increases in the assigned volume of C are shown in black, and such monotonic increases, which necessitate V's migration, are actually charged against the credit that V receives on its insertion. On the other hand, the credit that's assigned to V on its insertion is finite, right? It's roughly log K, but we can actually migrate many more times, right? As a result of C's component class or assigned volume decreasing and then increasing over time. So in such cases, V receives a credit for these non-monotonic changes, which could be increases or decreases. Uh, so V essentially receives credit from the deleted vertices in C to pay for such non-monotonic changes. So again, we have to only worry about monotonic increases, and this allows us to argue for log K competitiveness. Now, the next question we asked is, can we actually break the log K upper bound in the competitive ratio, assuming we have machine learned predictions? Okay. And the practical motivation stems from the fact that in practice, predictions on resource utilization in clusters or uh, the communication traffic between virtual machines can often be predicted to a certain desired level of accuracy. And as in many of the works and algorithms with predictions, the main question is what to predict, right? So in this work, we consider the epsilon accurate prediction setup, which is similar to a work by Gupta et al. From a few years ago. And in our OB-ADC problem, we consider the following predictions. So whenever a vertex is inserted at some time t, we assume that with probability eta greater than 0, a predicted set PV is revealed, where this predicted set contains the set of all vertices which are present at time t, and these are vertices which will be in V's component in the future. With probability 1 minus eta, we receive no prediction, and this predicted set is essentially empty. Okay, so if eta is 1, which means that we can perfectly predict which vertices are going to be in V's component, we ideally desire constant competitiveness. On the other hand, if eta tends to 0, which implies poor predictions, we want our algorithm to degrade to log K competitiveness, which matches the competitive ratio of our earlier algorithm, which was not augmented with any predictions. Our final theorem shows that we can obtain constant consistency and um, and we can obtain log 1 over eta robustness for our problem with predictions. In fact, the robustness is the minimum of log 1 over eta and log k, since for smaller etas, we want our algorithm to recover the competitiveness of our earlier unaugmented algorithm. Okay, so just for the sake of some intuition, how do such predictions help us? Well, the first thing to realize is that if we look at the probability of a merge request being incident to vertices in distinct components, Cj and Ci, this is a typo, sorry for that. So let S be the size of Cj without loss of generality. Let's assume that the size of Cj is at most the size of Ci. Then we can show by a simple argument that the probability that Cj is not equal to Ci is at most e to the minus eta times S. And the reason is that for at least S insertions of vertices, let's call these vertices W, all the predicted sets must have been empty. And since for a single predicted set to be empty, the probability is exponentially small in eta, the probability that at least S predicted sets are empty is at most uh, e to the minus eta times S. This captures the intuition that it's rather unlikely for a merge to happen between two components which are large enough, right? Okay, so given uh, this intuition, now we can again consider this graph, which shows the increases and decreases in either the assigned volumes or the component classes of C, where C denotes the component containing V at any given point. Okay. Let's call a merge monotonic for a vertex V if V is a part of the smaller component that's involved in the merge. And let's further refine this definition to say that a merge is monotonic if it leads to an increase in C's component class or C's assigned volume for the first time during V's lifetime. Right? So in this case, we can see that if these two times correspond to the insertions and deletions of vertex V, then all of these black edges denote monotonic merges for V. We bound the expected number of monotonic merges involving V by log of 1 over eta. Thus, in expectation, it suffices to assign a credit of roughly log 1 over eta versus log k in our earlier unaugmented setup. By utilizing a similar charging argument, we can show that this yields an algorithm which is log 1 over eta competitive. This essentially shows that if C is the smaller of the two distinct components, and it's involved in a monotonic merge request, then it can only happen log 1 over eta times in expectation during V's lifetime. For non-monotonic merges, we can use the credit left by the deleted vertices in C as before. And by combining the charging argument from before, we can obtain a comparative ratio, which is the minimum of log 1 over eta and log k. This shows that with predictions, we can significantly improve the competitiveness. In fact, for constant eta, we show that this is constant competitive. And a remarkable feature of our algorithm with predictions is that it uses all of the subroutines and invariants of our unaugmented algorithm. Okay, so this concludes my talk. Please feel free to get in touch via email if you have any questions or comments. I hope you enjoyed this presentation. Thank you.